right, so from our sort of only to this point minimal introduction to the idea of sort of working backwards along our brainwaves, and instead of thinking about derivative, but thinking about antiderivative, we've sort of observed a few things, which is, well, at least a couple things, I suppose. Well, a few, let's say a few. One thing is that, like, if you think of how to compute a derivative, the act of computing an antiderivatives can sort of be thought of very similarly to when you first started to divide numbers, thinking in terms of multiplication. So it's like, okay, 12 divided by 3. Okay, what times 3 gets you to 12? When you're trying to compute an antiderivative, you can sort of ask yourself, okay, what would be the function which would produce the given function with by derivative? Well, that would tell you what the antiderivative function would be. Okay, well, one of the things that we noticed is just like constant multiples are sort of simple to deal with derivative, constant multiples work wonderfully nice with antiderivatives as well, which is to say, just like a constant multiple is unaffected by derivative, the constant multiple would be unaffected by the antiderivative. Similarly, there was a very nice rule with respect to addition and subtraction, which was to say that, well, you know this with derivative, right? If you have two functional bits that are just added together, you just take the derivative of each bit and keep the plus sign in between. Well, then that would mean, with respect to the antiderivative of two functional bits separated by a plus or minus sign would be, well, simply taking the antiderivative of each of the bits, keeping the plus or minus sign in between. So an example of this would be, what if you were looking at the function 5x squared plus 7e to the x minus cosine x? What you notice here is this is a bunch of functional bits separated by plus or minus sign. In particular, some of these have constants in front. There happens to be a 5 in front of the x squared and a 7 in front of the e to the x, but just like you know, constant multiple would be unaffected by derivative, the constant multiple is going to be unaffected by the antiderivative as well. So the 7e to the x is just going to be, well, the 7, the constant multiple is going to be unaffected by the derivative. The only thing that unaffected by the antiderivative, the only thing that will be affected by the antiderivative is the e to the x. So if we sort of break the thing down, and we say, okay, we've got these bits that are added together or subtracted in the one case, well, then we can just look at each of the bits individually, and since two of the bits have a constant multiple, and we know constant multiples are unaffected, well, then we can focus our sights solely on the part of the function which is not related to the constant multiple, the part of the function which is actually functional in some sense, the part of the function which involves x. And then whenever you do this, we can sort of apply the rules that we've seen, which is to say, anytime you have x to a power, the antiderivative of that, you would ratchet up the power by 1 and put that power in the denominator, which is, well, what precisely the inverse operation to what you do with derivative. Derivative, you bring the power down and reduce the power by 1. Here you increase the power by 1 and put the power in the denominator, so we get 5x cubed over 3. What about the antiderivative of e to the x? Well, that's wonderfully nice, of course, because since the derivative of e to the x is e to the x, the antiderivative is also e to the x. And then here, we've got the antiderivative of cosine. Well, what the antiderivative of cosine, what function has a derivative of cosine? The function which has a derivative of cosine is sine. So that works sort of nice as well, and ultimately then we can cook up an antiderivative function, but we have to remember as well that if we have a function whose derivative is the original thing that was given, which is precisely what we do when we take an antiderivative, we know that while the function that comes out would have to involve a 5x cubed over 3 and a 7e to the x and a minus sine x in order to accommodate the terms of interest, we also know that there could be any constant added. So when we're looking at the functions who would, by way of derivative, produce the original function of interest, well then there would be infinitely many such functions because you could throw whatever constant you wanted on the end. And well, you get the same thing back in return. So we put the plus c there to sort of say, well, there could be any constant added. Okay, so we have some familiarity, some experience with this act of computing an antiderivative. And well, if you think about it, we had like a whole page worth of derivative rules. And you could then wonder, man, which of those derivative rules are we going to be able to look at to compute antiderivative rules? And perhaps the most commonly seen derivative rule that relates very nicely with antiderivatives is the chain rule. And remember what the chain rule says. The chain rule says, say you've got a function which doesn't just have a single variable inside. Say you've got something like sine x squared, not just a single variable, or e to the 5x plus 2. That's not just a single variable inside the e function. Tangent to the fifth x, that's not just an x inside our degree 5 function. That is a tangent inside our degree 5 function. So when we're talking about the chain rule, we're talking about a particular function which itself is inside another function. And we have gained familiarity with how to compute such a derivative, and well, as we know, we simply take the derivative of the outside function, leaving the inside alone, and then take the derivative of what was inside. So in the case of the sine x squared, when you take the derivative, you get cosine x squared times 2x. The cosine x squared taking the derivative of the outside function, leaving the inside function alone, and the 2x multiplying by the derivative of what's inside. The e to the 5x plus 2, take the derivative of the e function, well that just gives you a carbon copy, and then take the derivative of what was inside your e function, well the derivative of that would be 5. What about the tangent to the fifth x? Well, if we think of this sort of more in a more derivative-friendly form, we can think of this as tangent times itself 5 times, so then u is your tangent x. So whenever you take the derivative, you're going to get 5u to the fourth times u prime. 5 tangent to the fourth times secant squared being the derivative of tangent, of course. But now here's the thing to think about, and this is sort of the first observation I want us to make that's going to be like a brand new for the day, which is to say, if fu produces by derivative f prime u times u prime, well then the antiderivative is going to take you in the other direction. What the derivative does, the antiderivative undoes. So think about this. We can say the antiderivative of f prime u times u prime has got to be fu. The antiderivative of cosine x squared times 2x, the function which produces cosine x squared times 2x as its derivative, is precisely the function sine x squared. Well, I guess sine x squared is just one such function. That would be the function if we chose our possible constant of choice to be 0. And to that effect, actually, why don't we just come up here and plop in a c as well? But the idea is that if we had a statement which was taking the form of something that was produced by the chain rule, then we could go backwards along the chain rule to produce the original function. So, taking the same idea, if the derivative of e to the 5x plus 2 is e to the 5x plus 2 times 5, then the antiderivative of e to the 5x plus 2 times 5 is going to be e to the 5x plus 2, well, plus c, for the generality of the fact that, well, I mean, yes, e to the 5x plus 2 produces e to the 5x plus 2 times 5 by way of derivative, but of course e to the 5x plus 2 could have any additional constant added, and that would have dropped off by way of derivative. So to capture the antiderivative in full generality, we throw on the plus c. And the same story would apply here with this tangent function, and cumbersome and clunky as it may appear, ultimately we know from what we saw taking the derivative with the chain rule that this is something that results from the chain rule, and so we know what function it came from. It came from tangent to the fifth x, but of course we plop on the plus c to express that in full generality. And now, let me be very clear about the takeaway from this discussion of what we've done to this point. The takeaway is not that if you were simply given cosine x squared times 2x dx, that you would know what the antiderivative is, or if you were simply given e to the 5x plus 2 times 5 dx, that you would know what the antiderivative is. The purpose of this talk is to say, to this point at least, because let me be clear, until you watch the next couple videos, it's not going to be obvious how to compute that derivative, although we will learn the very technique that does it. But the point is that any function that gets produced by way of derivative would have an antiderivative. And so if you happen to be going down the derivative using the chain rule, then you could go back the antiderivative effectively using the corresponding antiderivative rule that would relate to the chain rule. And so the idea is what results from derivative, you could go backwards to find the antiderivative, and so the chain rule could be undone by way of antiderivative if you think in these terms. And what will sort of then, what you want to be thinking about, and what the direction that we'll sort of be heading is, okay, so how are we going to recognize when a function has been produced via the chain rule? And how can we go backwards to find the function that would have produced that function by way of the chain rule? Imagine that we hadn't taken the time to compute the derivatives that are now behind me. How could we have cooked up the antiderivative functions in each of these cases? Because I claim whenever we look at these functions from the right point of view, whenever we apply the proper mode of thinking and the proper technique on top of that, each of these and many more, frankly, will be doable.